Today we will start a new chapter, which is chapter 10 about spin, angular momentum. And we know very well that electrons carry spin, and they have two possible spin, say, angular momentum, which is plus or minus 1/2 of h bar. But this kind of doublet of this spin angular momentum was rooted in the earliest experiments by Stern and Gerlach in 1922. They performed experiments on this silver atom passing through this magnet. They carry magnetic moment or angular momentum, but when they pass through this magnet, there's a split of their trajectories into two different paths, and plus and minus trajectory, which corresponds to plus minus h bar of this angular momentum of the spins. Nowadays we know, and the similar experiments have been performed on the alkali atoms and passing through the magnets, and you could get exactly the same pattern that this atom beams got split into two trajectories and two paths. They are isotropic with respect to this central directions because of this kind of doublet nature of this kind of angular momentum. And we know that nowadays electrons carry spin. This kind of name attached to this angular momentum of, say, fermion particles, named after Pauli. So in 1924, Pauli proposed that electrons have two valued index associated with this, called the spin angular momentum or spin quantum number. There could be either plus or minus h bar as their values or eigenvalues. This is kind of intrinsic properties of electrons. But electrons are point-like. They are point-like particles. There's nothing that they can rotate about. So like a cartoon picture right here, you would borrow this classical picture of classical object spinning around this, say, z-axis, carrying angular momentum along the z-axis for electron. But electron is not a classical object, so it's a point-like particle. So electron cannot just spin around this like this, like ordinary balls, but we can only attach this kind of spin quantum number to the electrons when we talk about this angular momentum of, say, fermions. So the spins is really some kind of misleading, but nevertheless is kind of unavoidable name attached to this electron angular momentum. Electrons do not spin around this axis, but they carried intrinsic angular momentum. So it is the intrinsic properties of electrons, and the reason why Pauli makes such a proposal is precisely because of the Stern-Gerlach experiments. We don't know why the electrons carry spin, just like we don't know the origin of the gravitational force. Okay, the origin of the gravity is really a mystery. The only thing we know is that we have gravity, and this is the same thing. We don't know why electrons really carry the angular momentum, but they do, because this is what they told us they do, carry angular momentum. And they carry two types of angular momentum, plus and minus, and later this experiment can actually measure this amount of the magnetic moment in terms of h bar, and they do get such two values, plus or minus and half of h bar. And that's the origin of Pauli's proposal. As a result, we should consider the angular momentum of electrons as kind of intrinsic properties of electrons, and they carry two possible values. And therefore, we have spin operator, just like the orbital angular momentum that we studied before. And for spins, we also have a definition of an angular momentum operator for spin. And just like the orbital angular momentum operator, the spin angular momentum operator shows this commutation relations. Just like the orbital angular momentum operator, they have this commutation relations. So the only thing different here is that the eigenvalues for this S operator are different from this orbital angular momentum eigenvalues. Remember, the orbital angular momentum quantum number, L, is actually integer. But the spin operator quantum number could be, say, plus minus 1/2 h bar. In terms of these two eigenvalues, we could again define these eigenvectors, and we could define this eigenvectors. U corresponds to this eigenvectors of plus 1/2 h bar, or textbooks we call this chi plus, and chi minus is just 2x1 column matrix 0, 1, and chi plus is 1, 0. Okay, so you could expand this all the three components of the spin angular momentum operator in terms of this two spinners. Okay, 1, 0 or 0, 1. For example, this as Z is very easy to see that this is given by this simple 2x2 matrix where the diagonal matrix elements are precisely the eigenvalues, plus or minus 1/2 h bar. You could very easily check that as Z acting on this chi plus state gives you plus 1/2 h bar times chi plus. For minus, you get minus 1/2 h bar times chi minus. So then we could use this 2x2 matrix representation of this SZ operator and to construct all the others like Sx, Sy, and S plus, S minus, and so on and so forth. It is much easier to construct this 2x2 matrix for describing the spin operator than that, say, 3x3 matrices that we just studied in the previous chapters to describe the orbital angular momentum operator for L equals to 1. S plus and S minus, Sx, what? 1, 1, and Sy, 1/2 minus I. And so you could express the spin angular momentum operator in terms of so-called Pauli matrices. Okay, so sigma, the Pauli matrix, has three components: X and Y and Z. Okay, so you divide it. This Pauli matrix by your times sigma operators vectored by 1/2 h bar, you get the spin angular momentum operator. So you could check very easily that this kind of 2x2 matrix representation of the spin operator satisfy this commutation relations. And so you could rewrite this commutation relations between S in terms of the commutation relations between the sigmas, the Pauli matrices. If you square this Pauli matrix, you get unit matrix 1. It is a straightforward exercise for all of you to actually try to diagonalize this 2x2 Pauli matrices or this 2x2 S operators, S plus, S minus, Sx, and Sy, in terms of the eigenstates of Sz. So let's take a short break. When we come back, we will just do this exercise. So let's just talk about the generalized situation in terms of this eigenstates of this Sz. So as I mentioned, say two spinor 1, 0 state refers to this eigenstates of the Sz with plus 1/2 eigenvalue of h bar, and 0, 1 state is the eigenstates for minus 1/2 of h bar of Sz. But you could consider a general, arbitrary spinor. So this arbitrary state is what we emphasize millions of times, that this arbitrary quantum state could be written in terms of a linear superposition or linear combinations of orthogonal normalized eigenstates. Arbitrary state is a linear combination of the two eigenstates. And this is precisely the states that you note very well, the Schrödinger's cat story, that if this state 1, 0 refers to this living cat state, and 0, 1 state refers to the state that cat is dead, the Schrödinger says that before you open up the basket to check whether the cat is alive or dead, the cat states could be any states between alive and dead, which is a linear combinations of state 1, 0 and state 0, 1. And this is the simplest possible example of the qubit or quantum bit. By quantum mechanics, we are allowed to construct any arbitrary quantum states which is made of the linear combinations of two orthogonal eigenstates of certain operators. And this alpha plus alpha minus state is precisely this kind of arbitrary spinor that could be constructed based on this linear superposition principle, which is the principle so-called quantum computer. So the classical computer is made of 0 and 1s, but the quantum computer is based on so-called quantum bit or a qubit. So one single qubit can actually stores how much information that you could store. It's not just say 2 to the power of n, but you can imagine that the alpha plus and alpha minus are just complex numbers, and any combinations of 0, 1, and 1, 0 state could be your quantum state, or your qubit could be anything, as long as they are linear combinations of these two states, and that are the possible states of this qubit. So your qubit could actually store much more information than the classical bit can store. Okay, so this is the principle behind so-called quantum computer. But the problem is, or the question is, what kind of so-called two-level system that could really be used to construct a real quantum computer? Of course, we need to take advantage of the electron spin. But of course, a single electron state cannot be simply just a source of qubit, because you could not extract a single electron from the real solid state material. What can we do? So there are many possibilities that we can construct a spinor like this. But imagine that we could isolate this electron and we construct the linear combinations of these two eigenstates of Sz, and in that case we realize the qubit. But of course things are not that simple, but the idea is as simple as this. Any linear combinations of orthogonal eigenstates could be arbitrary spinor. This arbitrary spinor states is actually normalized states, which means that the square of these coefficients, alpha plus and alpha minus, when you sum up these two coefficients, you get 1. That this square of this coefficient, alpha plus square and alpha minus square, represents the probability that the measurement of the Z operator on the state alpha plus alpha minus gives you this plus or minus 1/2 h bar respectively, which means that alpha plus square is the probability that you take the measure of the Z on this initial state arbitrary state, which gives you plus 1/2 h bar as your measurement result. But of course, this is just a probability that you get this plus 1/2 h bar, but you also have this probability that you take the measurement of Sz on this state, but you receive this minus 1/2 h bar, which means that this coefficient square represents this probability that you take the measurement of this initial state of that Sz operator, where you could have this two possible scenarios. But how do you really get this probability? Well, you need to make millions of measurements. This is going back to our earlier statement, the very beginning of the course, that in quantum mechanics, eigenvalues and expectation values and measurements are all linked together. So the probability interpretation relies on the fact that you take many measurements. Each measurement you may have different answer, but that answers should be and must be one of the eigenvalues of this operator. I suppose you should be very familiar with those concepts. Okay, so you have many eigenvalues, eigenstates. When you take the measurement, the final outcome of your measurement could be only one of these eigenstates or eigenvalues that you find. You simply just take million times of measurements and you just count how many times that you get this eigenvalues, lambda 1 up to lambda n and so on. And you take the statistics, and this statistics tells you the probability that you take the measurement, what is the percentage that you get this value or that value. Okay, and this percentage is precisely the square of the coefficient representing. This is just a refresh of your basic concept of quantum mechanics. In general, we do not need to really keep this Sz operator diagonal. Remember, the Z is diagonal along, shows its non-zero eigenvalues along diagonal direction, but 0 along the other off-diagonal directions. But in general, we do not need to keep this Sz operator diagonal. So you could choose arbitrary eigenstates of this spin operators, like linear combinations of Sx and Sy with such cosine and sine coefficients, and you could diagonalize this matrix. You could find its eigenstates and eigenvalues. You could expand in terms of this eigenstates. Right? So I do not need to expand my Sz operator in terms of this 0, 1, and 1, 0 state, but I could form an arbitrary 2x2 matrix formed by this Sx and Sy operators or whatever operators I like, and you find eigenstates, eigenvalues, then you could construct the 2x2 matrix based on the eigenstates of that operator. So let's try to diagonalize this, generalize this 2x2 operator for a spin angular momentum. Suppose you know this 2x2 matrix representation of this Sx and Sy, and you simply just multiply those operators by the cosine and sine phi to try to solve the eigenvalue equation. Okay, so the magnitude of these eigenvalues must be 1/2 h bar, but the problem is the sign, the lambda is plus minus 1. This is your eigenvalue equation, and you could very easily solve for this 2x2 eigenvalues and eigenvectors. Okay, so you simply just plug in this definition of the Sx and Sy operators that we just defined earlier and plug in here, and you get this 2x2 matrices, and then you cancel on two sides of the equation this 1/2 h bar, you get this eigenvalue equation. This is really easy to solve. You get lambda plus minus 1, and then you get eigenvectors for plus you get this. For minus, you get this. This is for lambda is plus 1, and this is for minus 1. Okay, but you could multiply those two eigenvectors by a phase, and this could still, they are still the eigenvectors. You could multiply everything by e to the minus I phi over 2. The reason why we do this is just for the purpose of a symmetry. Now those two components of the spinor looks symmetric. E to the minus and plus 1/2 of I times phi. So this u minus under such a redefinition. Okay, so you could check that this u plus and u minus really are orthogonal 0. This is 1, and this is 1 times minus 1 is minus 1, so 1 minus 1 is 0. Okay, so indeed these two states are orthogonal. And you can construct this S operator, Sx, 1, and z, in terms of this u plus and u minus states. Okay, well, you could check that. Okay, so very easy to check and to construct this new 2x2 matrix representation of the spin angular momentum operator, but you expand this operators not in terms of this eigenstates of that z, but eigenstates of this new operator, this one. Of course, when you do so, this Sx will not be simply just what? The one that you just defined. And Sy will not be this guy. Of course, Sz will not be this. But even so, their commutation relations are exactly the same. And this exercise tells us that the eigenstates that you expand about this operator are totally up to you or up to us. So we don't need to really choose this 1, 0, 0, 1 state as our eigenstate to expand all these operators in terms of matrices, but we could choose arbitrary, the eigenstates of arbitrary linear combinations of this spin operators, and then we expand this, the new matrix representation of the spin operator in terms of the new eigenstates. So let's take a very short break, and when we come back, we will try to calculate this excitation value, the three spin angular momentum operators given by any arbitrary initial state. 所以这边呢，这个电子的自旋这个 chapter 其实就是我们之前所有的 chapter 的一个可以说总复习吧，那是一个特别简单的2×2的矩阵可以来描述的量子力学系统，是最简单的，就是一个 electron spin 1/2的 system。但是呢，它包含了所有我们这堂课提过的这个概念，包括测量，包括期望值，包括几率，然后你可以有 arbitrary 的 quantum state， 你也可以有本征态 eigenstate， 你可以连续做好几次的测量第一次测量的结果，然后你再做第二次测量，这2次测量会得到某一个 eigenvalue 的几率是怎么计算那这我们都提过了那只不过这边就是用一个非常简单的2×2矩阵来计算而已那个概念都是一样的概念。We are able to calculate this excitation value of Sx, Sy, and Sz sandwiched by any arbitrary spinor state, alpha, which is defined here with two components in their matrix elements. Alpha plus is the top component matrix element, and alpha minus the second matrix element. In terms of these matrices, you could very easily evaluate this excitation value of the Sx operator. You can simply just, plug in this definition of this Dirac-Brand cascade of this spinor alpha, and you get this broad state, and this is cascade, and in between you insert this SX matrix. And this is just a simple exercise that you multiply the three matrices together. What you get is the number. Okay, so this number represents the expression value of SX operator when you make such a kind of a calculation, perform such a calculation on an arbitrary state, which means that if you have a given initial state labeled by alpha, and the question is what is the expectation value of SX operator, which means that you take the measurement many times, and what is the expectation value of this measurement for SX? This is the expectation value. So likewise, you could calculate this SY expectation value in the same manner that you simply just construct this 2x2 matrix and this Dirac-Brown-Cat state, sandwich this SY, and you get this number. And at Z, you get this number. So now you are able to calculate this expectation value of any spin operators, any component of the spin operators given by any arbitrary initial spinor state. Our textbooks discuss the example, which is more or less what I just mentioned. So a measurement of Sx for spin 1/2 system leads to eigenvalues plus 1/2 h bar. A second measurement following the first one, but this time the second measurement is not of Sx operator, but is of this generalized operator or any other arbitrary spin 1/2 operator that you can form by a linear combinations of Sx, Sy, and Sz. Here it is Sx cosine phi plus Sy sine phi. This kind of a second operator that you need to measure the eigenvalue. So the second measurement is carried out. So the question is, what is the probability that the second measurement gives you still plus 1/2 h bar? What is the probability? So let's just do the simple exercise. So we know that this first measurement, when it's down, the result is actually plus 1/2 h bar, which means that this, after the first measurement, the states evolves from the initial state to this eigenstate of the plus 1/2 h bar of Sz. So, but we know that this Sx operator is given by what? This guy. I will finish this on Wednesday, and probably we are done. You could also check our textbooks, and I am sure that you are able to carry out this exercise by yourself. But let's discuss the remaining part of the exercise next time.